So really, the only reason we do this is because we're trying to find out the OH alkalinity. As you know, we want to make sure that we have enough to control any sort of acid that might appear, but also we want to promote scale precipitation. We had the magnesium hydroxide and the carboxy, pardon me, not carboxy, hydroxy apatite. But we want to make sure we don't have too much because high pH is aggressive toward boiler steel. So we're going to have corrosion, maybe interdeposit corrosion, wick boiling, caustic gouging, caustic embrittlement, all that kind of stuff. So we want to control the OH. We want to maintain it within a control range. And for a lot of the boilers that you see, like say the SAIT boilers, maybe say 150 to 300 ppm. Now, really it depends upon the plant and upon the water treatment rep, and our job then is just to maintain it within a particular range. So how do we know? We do it 2P minus M, and it gives us OH alkalinity. Now, we can also use it to determine carbonate alkalinity, and so then that's the potential for condensate line corrosion. And it'll tell us, kind of how much amine to feed into the system. And those amines, neutralizing or filming amine. So, this is what we're trying to do with the PNM alkalinity test. Now, a lot of plants don't actually do the CO3 calculation. A lot will do the hydroxyl, but some don't. But if you want to kind of be a smarty pants in your power plant, you can always do that just for kicks and giggles. Then the next thing is dissolved solids. Well, here it says total dissolved solids, specific conductance, conductivity. It's not really the same, but if you recall, we said that conductivity and total dissolved solids, there is kind of a relationship. It's a pretty good relationship until we get some weird stuff in there, like sodium ions really affect the nature of that curve. But we use this very commonly to figure out what are the dissolved solids. Basically, how conductive is the water? If the water is highly conductive, we can convert that into a dissolved solids number. If it's not very conductive, we got low dissolved solids. And so when we mention dissolved solids, what in fact are they? It's anything dissolved in the water. But the ones that are important mostly are those that we call alkalinity. So bicarbonates, carbonates, salts, that's alkalinity. Now, we don't want excessive alkalinity because, we get foaming, carryover, that sort of stuff. But this is not directly an alkalinity test, okay? So TDS or conductivity does not tell us exactly what species are present dissolved in water. Basically, it just tells us that the boiler water is really, really soupy. It's really thick and chewy, or it's nice and clean. If we find we've got high TDS, well, we might want to examine a little bit further and see exactly what is a dissolved solid in the boiler water. Is it a form of alkalinity that's high, or various hardnesses, calcium and magnesium, are also dissolved solids. And we can get other stuff in there too. So let's say we've got sodium Na2SO3. That's a dissolved solid. It's an oxygen scavenger, but it's a dissolved solid. Or maybe we've got Na2SO4. Again, it's a dissolved solid. it's neither hardness nor is it alkaline. So basically, if we take anything that's dissolved, whether it's alkaline, whether it's hardness, or something else, that will affect the conductivity, and we can use something like this here, which is called a SoluBridge, which is a really cool, old school piece of equipment. And basically, it's got a red light, and it's got a little green light. I won't mess it up with my pen. And it's got a scale, and the scale says meg ohms per centimeters at 25 degrees. What we'll do is you'll have it in micro Siemens. And this here is like 1959 technology, but don't be surprised if you still see it in your plant. It's really, really a cool piece of equipment. All you do is you turn this dial this way or that way while you have a probe in the water. Okay, so you've got a water sample, you got the probe in the water, and you just turn the dial back and forth until both lights glow at about the same intensity, and then you just read right off of the dial. So it's just a cool old school piece of equipment that's still in use. So inside of our boiler, we got a certain amount of dissolved solids in there, and we got feed water coming in that has relatively few dissolved solids, and then we've got our continuous blowdown line. And if I take a look at the concentration in the boiler water and I divide that by the concentration of the water coming in, that'll tell us how concentrated the boiler water is. So we call that cycles of concentration. And typically a water treatment rep is going to have you run your boiler, or frankly, even if it's a cooling tower, they'll say that we want you to operate at so many cycles of concentration. So in order to do that, we need to know the TDS here and the TDS there, and and knowing that, we know how concentrated the boiler water is. So let's say that our TDS of what's going out is 3,000 ppm, and what's going in is 10 ppm. Then what we would have is the cycles of concentration of 3,000 over 10, which would be equal to 300 cycles of concentration. Now, TDS, like I said, is not a very good way, or pardon me, I should say conductivity is not a very good way of determining TDS because of sodium and chlorides and things like that. So certain ions aren't very conducive for determining what the actual dissolved solids concentration is, because conductivity will be affected by those ions. So if we have got chloride ions coming in, then that's non-scale forming, it's not alkaline, it's kind of neutral in terms of what it does. We could get chloride stress corrosion cracking, but that really only happens in stainless steel. It's not a big factor in carbon steel. So really, this stuff here, these chloride ions have a neutral effect on the boiler water. Of course, understand it's not magnesium chloride or calcium chloride, which would be scale forming. No, but if it's sodium chloride, it's not going to cause us a problem. So if we measure the chloride ions coming in and we measure the chloride ions leaving, we can more accurately determine the cycles of concentration. Is that a question? I heard a bloop. let me just get out of this for a moment then. And it could be that people are having trouble hearing me. No, I don't see a hand up. Oh, I know what it is. I got my mail open. So I guess some mail just arrived. So I just closed that. Okay. Where were we? We were cycles of concentration. So what we can do then is take our chloride. Oops, forgot to turn on my pen. We can take the chloride ion concentrations instead of using conductivity. We can have a chloride ion concentration in the boiler water and the chloride ion concentration in the makeup water. It's a much more accurate way of determining the cycles of concentration of the boiler water. As for doing that chloride test, I've never worked in a plant where the engineers have done the chloride ion test. It is in your textbook, but now you know what it's used for. The only places that I've worked at where they've done the chloride ion test, it was done by the water treatment rep when that rep showed up. Okay, the next thing is our good old pH scale, and I'm not going to spend a lot of time on that, and you know why we do a pH test. You know, so we want to control acid, we want to control caustic attack, we want to maintain in that safe pH range, and you know, we also want to make sure that our pH is high enough that a coordinated phosphate program is going to work at eliminating any scale forming compounds that come in. So the one thing to remember really is that the scale is logarithmic. So if I go from pH of 7 here down to a pH of 6, what we get is a tenfold increase in the number of protons. There we go. We go from 10 to the minus 7 to 10 to the minus 6. That's what the 6 and the 7 mean. It's the exponent. And so it's a logarithmic scale. So don't go, the pH only changed by 1. What do you mean it changed by 1? 1 is a lot. So just keep that in mind. How do we measure pH? Usually we've got some sort of a pH meter, and we'll have a probe, sort of like what we do with conductivity, and we put the sample inside of a beaker, we stick the probe in there, press a button, there we go, you got pH reading. 10.2 there. See, it even works. So chlorides, now you know what they're used for. You might not have many chlorides in the feed water, and if you don't have a lot of chlorides in the feed water, they won't even bother with the test. Well, when do you get chlorides? When sodium zeolite softening is used, basically, you know, because we've got magnesium chloride and we've got calcium chloride entering into the sodium zeolite softener, and what we get then is sodium chloride leaving there, balanced-ish. Or maybe I'll go like this too. They're balanced, both the calcium and the magnesium. Okay, so here, this is our feed water now, our makeup water. We've got chloride, we've got chloride. We don't really care too much. It's not scale forming because it's a sodium compound. So we can measure it if it's coming in, if we've got a sodium zeolite softener. You know, chlorides definitely contribute to total dissolved solids. They increase in the concentration as we operate the boiler, and because of that, it's useful for determining cycles of concentration. And we can also use it for determining percent blowdown. And percent blowdown, if you recall, is how much water is being blown off compared to how much water is flowing into the boiler. Now, there's a test in your textbook. I've never done it in my life, in my career. You can read it over and familiarize yourself with it. Did any of you do a chloride ion test last year in lab? Yes, no? Is it something that we do in our lab in year one? I guess not. So then a whole bunch of other tests that you can read over. Iron test, dissolved oxygen test, steam purity test. Read it over on your own. There's all sorts of ways nowadays, like when you get into a more sophisticated plant, we've got all kinds of automatic monitors, online real-time dissolved silica monitoring, all kinds of interesting stuff. If you wanted to learn a little bit more about that stuff, you can go onto the Hach website, and Hach is a big name in online water analysis. But read over that stuff on your own too. I'm not going to go over it. Now then, chemical feed systems. Okay, I wanted to get into this because from an operational standpoint, there's a few little gems that I'd like to share with you. Maybe some practical kind of stuff, okay? So the first item in this thing was pot feeders, and you know that's covered in 4th class. I really don't want to go over it again. But what we're going to look at today is the day tanks and neat chemical addition, which is what we have in the Synovus building. So a day tank is a tank that you fill up once a day with chemicals. I don't even really want to go over the slide. I want to go over this slide here. Okay, so here we've got 3 day tanks, and there is a bit of a glitch in your Penn Global as to where some of these chemicals are going to go. So for example, here we've got sodium sulfite in this large tank, and I'm not too sure where they had it being fed to, but this is where we are going to feed it to. We're going to feed sodium sulfite to the deaerator. That's where it's going to go. By feeding it to the deaerator, we also protect the feed water suction pipe. And that's what we want to do. We want to protect not just the boiler, but we want to protect the feed water lines. Well, where's the best place to deaerate chemically? The place where we're doing it mechanically. So we end up protecting both the deaerator, the feed water lines, and the boiler proper. So make that correction to the diagram that's in your textbook. Here we've got another one here that says neutralizing and filming amines, and we know this is for return line corrosion prevention. And I'm not too sure in the textbook where they're feeding that to. I think they're feeding it to the boiler drum, or maybe they're feeding it downstream of the boiler feed pump or something like that. There's a problem is because this stuff here is expensive, and it does nothing for the boiler. It does nothing. It doesn't help prevent corrosion in the boiler. It does nothing. The boiler's job is just to evaporate it so it travels with the steam and so that it can get to the condensate return lines. So if we feed that into the boiler, every time we do a continuous, we operate the continuous blowdown, and every time we do a bottom blow off, we blow these chemicals into the blow-off tank and down into the sewer, and what a waste of money. And what a waste of chemical. So where plants are normally injecting this stuff is into the main steam header. So what that means, if I got a boiler here, and I got a steam line going into, say, a main distribution header, you know, this one's going to one part of the plant, this one's going to another part of the plant, blah, blah, blah. Okay, so here's our main steam header. And what I'm going to do is inject it, say, right into there. as soon as it goes into the steam line, it's going to volatilize. It's going to immediately evaporate due to the temperature of the steam. Then it gets carried through and unaffected by blowdown. So make that correction too. In your textbook, make sure it says in the diagram that this stuff is being injected most preferably into the main steam header. Now, it doesn't mean that there aren't plants where they inject it into the boiler, but usually a water treatment rep will encourage the chief engineer to change the injection location into the steam header. Unless, of course, that water treatment rep is a scoundrel and just wants to sell more and more chemicals, knowing damn well that the stuff's going down the drain, but there are people like that, I guess. Now, this one here is really cool. I like this. They've got this particular chemical, phosphates and sludge conditioners. And the phosphates and sludge conditioners, they have them being fed into the suction inlet of the boiler feed water pump, which sounds pretty cool. Of course, usually we've got multiple boiler feed water pumps, and so you've got one that's in operation and the other one's in standby. So you'd have to make sure that you switch it over when you switch over the pumps. But it's a good idea to actually inject this chemical into the inlet of the pump because the impeller acts as a really good mixer and ensures thorough mixing of the chemicals with the water. So, well, here's the problem. Okay, so we've got all of this stuff being injected into the various locations. We've got chemical feed pumps, and we've got check valves, and we've got a standby chemical feed pump in case the first one packs it in. We can bring on the second one, and usually what we'll do is we'll rotate them maybe on a monthly basis. So in December we run this one here, and then January we run that one there too. I mean, that's one strategy for dealing with all kinds of pumps and compressors and all that kind of thing, is to rotate their activity, say, every month, and that way each piece of equipment gets even wear and tear, plus that the standby piece of equipment is actually functioning, ready to go. Okay, so each one of these has a couple of different pumps. So here's where the problem comes in, is how do you adjust the feed? Do you adjust the feed by changing the concentration? Or alternately, you can say, well, if I need to change the feed rate of chemical, do I change the speed of the pump? So we've got two options here. So let's say we're a little bit low on phosphate. Do we make the phosphate stronger in the barrel, or do we increase the pump speed or the pump stroke, whatever it happens to be? Any ideas? I think this is worthy of a bit of conversation.
Wouldn't it generally be more accurate to adjust the feed rate of the pump than adding more chemical and being off in your measurement?
Okay, so this is a good point. Is that okay? So if maybe when the tank is, why did I do that? Maybe when the tank is full, that's full, and what we can do is right on the side of it, add so much phosphate and add so much sludge conditioner, after you fill up the tank. So let's say that, on the previous shift, the tank level goes down to there. So what you do is you fill it up and then you add so much chemical. But wait a minute, maybe you've added too much chemical. Maybe you've made it too concentrated. maybe the amount that's written on the tank is for when the tank is completely empty and you completely fill it up, you add so much chemical to it. You know, that's a bit of a problem. There's the whole kind of delay factor, you know, so how much chemical do I add to this tank in order to get the desired effect in the boiler? I mean, it's really hard to say because there's a dilution effect of all the stuff that's remaining in the tank, and then you're going to add extra chemical. Well, how much extra chemical do you add? And then does it make sense to increase the concentration of the chemical in the whole tank when maybe that amount of chemical won't be necessary to actually adjust the phosphate in the boiler? So I think that that's kind of where you're going with that, right? It's kind of inaccurate and it's kind of sloppy. So it's better that we adjust the pump speed or the pump stroke, one or the other. You need more chemical, you make the chemical feed pump go at a faster rate, or you need more chemical, you increase the stroke of the pump. These are the two ways that we change the feed rate of these pumps. Which means then that we're going to try and keep a constant chemical concentration. So what we do then is we'll have a whole bunch of graduations on the tank. And it really depends how low the tank gets. And so maybe if, you know, over a period of 24 hours, this tank only gets down to this level. And it'll say, you know, add 50 milliliters of amine. And then this one here says add 100 milliliters of amine. So when you go into a tank, you'll see where they have day tanks, they'll usually have marks on the tank, and the marks on the tank are going to be evenly spaced, and one is going to have some little comment about how much of the chemical to add, and the whole idea is to maintain a constant concentration. So now it doesn't matter whether you come in on shift and the tank is pumped down that low, or if you come on shift and the tank is pumped down that low, you can look at what the level is and figure out, well, how much chemical do I need to add? And then the rest of it will just be water, and you raise it back up to its normal full level. Then if you find out that you're low on phosphate or you're low on sulfite or whatever, then you just adjust the pump speed. Okay, does that make sense? Because I'm kind of babbling here this morning. So the problem is then, how do people deal with the concentration? And I didn't catch who made the comment, but he was saying something about, well, you know, individual operators can be, you know, a little sloppy, you know, the way that they measure the chemical. Operator A measures the chemical accurately, and operator B, you know, is kind of sloppy with the chemical measurement. And, you know, maybe operator C always likes to add an extra cup full of this chemical because, you know, if a little bit of chemical is good, then lots of chemical is even better. This type of stuff. So it introduces operator error. But that being said, day tanks are very, very common. But if I want to get rid of operator error altogether, I can go to a neat system. So I don't know if anybody drinks alcohol here, but you know, some people will say, well, I drink my scotch neat. What neat means is that you haven't added anything to it. You haven't added water to it. You haven't added, you know, a mix. You haven't added anything to it. You just drink it the way it came out of the bottle. And so I think that maybe that's where they got this term neat from. Neat really means that you're just going to add unmixed chemical. And that's what we got going on in the on the main floor of the Synovus building. So we add the concentrated chemical as received, no dilution, no mixing. We pump directly from the container. And the cool thing is we don't have to handle the chemical. We don't have to mix it. We don't have to, we're not going to get splashed with it. Yeah, we're going to wear our PPE. We're going to wear our aprons, our gloves, and our face shields and stuff like that. But less chance of having the stuff land on your skin or getting in your eyes, that type of stuff. Now, there's no variation in concentration. It's going to be constant. So now all that we have to do is adjust the feed rate according to the test results. Now, when the container gets low, we just change out the container. So this is a neat system. Oops, what happened there? This is a neat system. So there's our phosphate and sludge conditioner and dispersant. Here's our sulfite in another one, and here's our amines in another tank. And each one of these tanks, you can see it might not have a gauge glass on it, just simply a poly tank, and you can actually see the level of the liquid inside the tank. And so then we've got an isolation valve, and we've got a hose that's connected to it. Now, did anybody work in industry in the summertime where they had to do pump drawdowns?
Yeah.
Yeah.
You loved doing pump drawdowns, didn't you?
Oh yeah.
Okay, so for those who don't know what a pump drawdown is, here's our chemical feed pump. And, maybe it's got a little adjustment knob, or maybe the control room is going to change the pump stroke or the pump speed, right? But anyway, so somebody somewhere has done a test and says, oh, we need more phosphate. Okay, how much more do we need? Well, right now, our current feed rate is, 50 milliliters per minute, and I want it to be 60 milliliters per minute. Oh, okay. So what you have then is a couple of valves here. You got this one here, which is showing open, and you got this one here, which is closed, and this really is a graduated cylinder that's connected to the bottom, to the chemical. So what I do is I take my little timer, my little stop-start timer thing, and what I'm going to do is just very carefully open up this valve here and watch the level come up to its 0 mark, at which point I'm going to shut that valve. Now I got the timer ready, and I'm going to flip the valves and start the timer, and over a period of, 30 seconds, I'm going to see how much it draws down. So I do a 30-second drawdown, and I record the number, and then I flip the valves back into the normal operating position. And maybe you didn't quite get it right, so you might have to do this 5 times for each chemical to get the drawdowns correct. Is this bringing back memories, guys?
Yeah.
Yeah. And then after a little while, these chemical totes, they get low, so you kind of, it gets really, really low to the bottom. And then what we'll do is turn off the pumps, isolate it, and we'll disconnect the hosing, and, somebody will come along with a fork truck and take out the old tank, put in a new tank, and then they'll drain what was left over in the old tank. They'll drain it into the new tank. You hook it all up, you get it going, you do another drawdown just to verify that it's doing the proper amount. So that's called a drawdown. And yeah, a good chunk of your shift could be doing stupid drawdowns. Okay, certain advantages. And as for chemical totes, you know, larger chemical totes look like this. So they got a place here where a fork truck can put their what do you call them? The sticky outy parts of the forklift, and so you can lift them up. I mean, they come. They're going to be full of liquid to about there, and you can see it's a poly tank, so you can see what the level is. And it's got a valve here. Okay, and that's where you'd hook up the hose that goes to the drawdown, and then there's a vent up here, so you got to make sure you open up the vent. And depends what the chemical is. It might be sensitive to air, so you might have to put some kind of a desiccant filtration unit on top, so that as it draws in air, it dries out the air, so that the moisture doesn't affect it. Blah blah blah. But anyway, it's just one of the fun things about working in a plant that's got large, neat containers. With that, I think we're done internal treatment. Any of the guys who worked in industry have any comments about this neat system?
Yeah, it's nicer because then if you have a day tank, you don't have to worry about forgetting to fill it.
Yeah, exactly. Yeah, it's pretty simple actually. My suggestion is if you end up working in a SAGD plant or something like that where they've got these large chemical totes, usually you have to have a fork truck license in order to change them out. And so look into getting your fork truck license in any plant where you work. It could be very helpful. And what it does is it makes you a little bit more valuable on shift. So I know I was often the only guy on shift that had a fork truck license, and so I could go around the plant and change chemical totes for people.